Hi everyone, I'm Dennis Fang with Rigetti Computing, and today I'll be talking about fabrication tolerances for traveling wave parametric amplifiers, or TWPAs. So the motivation behind this talk is that building a Josephson TWPA requires precise fabrication. That's because a TWPA is essentially a nonlinear lumped element transmission line, which has hundreds or thousands of unit cells, which are all nominally identical or precisely controlled in circuit value. So in a realistic setting, you'll always have fabrication spread, and here we'll study the fabrication tolerances of these circuit elements. So let's start by looking at the TWPA unit cell, and highlighted in green are the main transmission line elements. LJ represents the Josephson junction, or JJ, and CJ is the parallel capacitance. C is the shunt capacitance to ground. So in order to optimize the gain in a TWPA, you always need a technique to phase match the propagating waves along the TWPA. Here we use a method developed by UC Berkeley, which capacitively couples a resonator in each unit cell. And there are other methods to do this phase matching, like modulating the impedance along the length of the TWPA array, done by groups listed below. Here we show some cross-sectional stack-ups of our elements. So our JJs are developed by a double angle evaporation process, and our capacitors, depending on the capacitance value, are either parallel plate capacitors or planar capacitors. So let's begin the analysis by looking at identical unit cells. So it's known in the literature that the signal amplification can be solved by the TWPA circuit wave equation, and the resultant gain is exponential with respect to G and X, where X is the length of the TWPA and G is the gain coefficient. This gain coefficient is a function of some kappa coupling terms and this delta K phase mismatch term, but importantly, these terms depend on the dispersion relation K of omega, which is wave number as a function of frequency, specifically at the signal, idler, and pump frequencies. So given that, we decided to capture cell-to-cell variation in a numerical calculation of the dispersion relation. So to analyze the effect of variation on our gain, we employ the following method. First, we emulate fab variation by randomly sampling from assumed normal distributions. Here, we've chosen two circuit elements, LJ and C. We've added in some spread around them, sampled from those normal distributions. Second, we construct a transmission matrix for each unit cell. So each of these two-port networks, which are unit cells, can be converted systematically into a 2x2 matrix, which depends on the exact circuit values. Next, we cascade the unit cells together by simply multiplying their matrices, and we convert to a total scattering matrix. We take the scattering matrix, we take the phase of it, and extract the dispersion relation. And that's because the wave number is simply proportional to the total phase accrued across the TWPA. Then we insert dispersion relation into the aforementioned gain expression as a first-order perturbative approximation. And finally, we repeat many times to obtain statistics on the gain. So let's apply this analysis to our phase matching resonators. Here we have our model dispersion relation and model gain profile. And into the dispersion, we see this sort of linear slope here. That's just from the transmission line part. And we see this pole here that's opened up by the resonators. We optimize our pump frequency around this resonator region in order to maximize gain. That's how we produce this gain profile here, noting that the pole is roughly in the same place as in the dispersion relation. So let's zoom in a little bit to the dispersion. And we see that near the resonators, we have this sort of wide curvature here And that's actually what allows us to tune the pump frequency in order to maximize gain. Then we apply the numerical dispersion method once. So we have 1% on our CR. And we see that we don't get much change in the linear parts of this curve, but it does open the single pole up into a spread of resonators, which is essentially a band gap. And that actually limits our curvature on the side here, which limits the amounts of that our pump frequency can optimize gain. That's one of the reasons that we see this drop in gain over here. So we can repeat this many times, in this case 30 times, and dark blue represents our mean curves, and the light blue ribbons around it are the standard deviations. Using this model, we can see that as we increase the spread in CR, our gain drops monotonically. And if we denote a -3 dB threshold, our tolerance with respect to that is 1.7%. We also learned from this model that if we increase CC, which is our coupling capacitance to the resonators, we have a higher tolerance to the CR and LR. We can see that as these curves get less and less steep as we increase the CC. So this is intuitively because the more coupling we have to the resonators, the wider curvature we have in the dispersion, and which essentially compensates for the fact that you have a wider spread in your resonators. So next we analyze defects in our JJs. We supplement the previous analysis with a transmission amplitude analysis. That's because we know JJ defects will introduce impedance mismatches along the line, which affects transmission amplitude. So the process for this is that we take the scattering matrix and extract the amplitude instead of phase from it. And we look at the loss that we get. So we look at 3 different types of defects. One is spread around a nominal LJ. Next is rate of JJ shorts, and also the number of JJ opens. So we see that in the LJ spread case, our tolerance is actually quite good. It's above 15%. But our JJ shorts have lower tolerance at around 5%. And even a single open will ruin the transmission of the whole array because it essentially disconnects the signal line. To compare with the sensitivity analysis discussed, we measure the fabrication spread at room temperature. So in this case, we measure test structures of CR. And initially, we started with a PECVD process to fabricate the dielectric of the parallel plate capacitor. But we see that even with varying plate areas, our spread isn't consistently under the tolerance calculated, which actually motivated our move towards an ALD process to create the dielectrics. We see that with higher plate areas, we have spreads that are consistently under the tolerance. And this is actually where we've tuned up our process. We've also measured our JJ resistances at room temp, which is actually proportional to the LJ inductances at cryo through the Ambergalker-Bertov ratio. And we've measured many test structures of many different JJ sizes. And we see that our spread is under 4%, which is well below the 15% threshold discussed earlier. On the right, we have wafer scale resistances. Color represents resistance. And each of these lines is actually a line of dots, which is one chip of 800 junctions. And we see that, so we have red dots, which are opens, and black dots, black squares, which are shorts. And even with all this scatter of defects, we still have a relatively high yield of defect-free chips, 32 out of 42. So finally, we measure these TWPAs cryogenically. On the top left, we see one of our TWPAs wire bonded to its PCB inside copper packaging. And on the right, we see these TWPAs mounted in the mixing chamber stage in the dilution fridge. We've measured the dispersion and gain profile of these TWPAs. And we see it in the dispersion, we do see this sort of like spread of resonators, and also its curvature around. And in the gain, we see a gain of above 20 dB over a band of at least 500 megahertz. And we still see these ripples in the profile because of some impedance mismatches. So in summary, we've introduced the numerical dispersion the numerical dispersion method, which captures cell-to-cell variation in the dispersion relation. We've used this method to analyze fabrication tolerance of certain circuit elements. And this analysis has motivated design changes to ultimately produce experimental devices with strong gain performance. Thank you.